This lecture introduces the reduced row echelon form of a matrix. Reduced row echelon form. Okay. So if a matrix is had to be reduced row echelon form, if first the matrix is in the row echelon form, right? So you have to make sure that the matrix is in the row echelon form, and then the next things that you need to do is you need to make sure that the first non-zero entry in each row is the only non-zero entry in each column. For example, if you look at this matrix A, 3 by 4 matrix, right? And you will see that the first, the leading non-zero leading entry of each row is 1. Okay, so that's the first condition for a matrix to be in the row echelon form. Second, the number of leading zero entries in each row is more than the number of the leading zero entry in the row above it. So that's the second condition, right? And the last conditions is all the zero rows has to be in the bottom of the matrix, which we don't have any zero row here. So this matrix here first is in the row echelon form. And the next thing that we need to make sure is to make sure that if 1 here is the first non-zero entry in row 1, and this entry here is row in the first column, and also this one here is the only non-zero entry of the first column. Go to the second row. This one here is the first non-zero entry of the second row. Also, if you look at the first column, it is also the only non-zero entry of the second column. Go to the third row. 1 here is the first non-zero entry of the third row. If you look at the fourth column, it is also the non-zero entry of the fourth column, the only one. Okay, so that's why A is in the reduced row echelon form. All right. And now we can talk about a couple new terminologies. So the first terminology is the pivot positions. As you can see that in matrix A here, 1, this positions here, this position here, and this position here, they are pivot positions because there are locations, right? Locations of the matrix A where that corresponds to the 1 as the non-zero leading entries of each row. So this pivot positions here is a position 1, 1, right? First row, first column. This position here is in the position 2, 2, which is second row, second column. And this position corresponds to the positions of 4, 3, because it's on the fourth of the 3, 4, because it's on the third row and the fourth column. So you determine pivot positions based on the 1 entries of the reduced row echelon form. Okay, so then using this pivot position, you can determine pivot column. So pivot column is a column of a matrix A that contains the pivot positions. So in this case, I know that the first column is the pivot column, right? Because this column here contains 1 pivot position. Also, the second column is another pivot column, and the fourth column is another pivot column of matrix A. Okay. So these are pivot column 1, column 2, column 3, and then these 3 values here are the pivot positions in a reduced row echelon form. So how can we get to, how can we obtain a reduced row echelon form of a matrix? There's an algorithm is called Gauss-Jordan reductions. And this is an algorithm, or is the process of using elementary row operations to transform a matrix into its reduced row echelon form. Again, this is the algorithm, or is a process that helps us transform one matrix, any matrix, into its reduced row echelon form. So the process of this algorithm is, first, you start at the leftmost non-zero column. Okay, this is a pivot column. So for example, if I have a matrix, right, an arbitrary matrix, let's say 4 by 4 matrix, or 3 by 4, 4 by 4 matrix here. Okay. And then I want to reduce this matrix to, let's call matrix A, and I want to reduce this matrix to its reduced row echelon form. First, I want to start with the leftmost non-zero column. So let's say if I have this column here is the leftmost column, and if it contains at least one non-zero entry, it is going to be the leftmost non-zero column. Okay, or let's say this is a non-zero entry. First column, first row is a non-zero entry. First thing you want to do is you want to pick it, right? And and then you pick the leftmost non-zero column, and then you choose the entry you want it to be in the top, which is in the pivot position. So I want to pick this as a pivot position. Remember, you can try to make this equals to 1 at first. All right, I can use one of the row operations to make this pivot positions to be 1. Okay, and then I will use all the row operations to make all the entries below this pivot positions become 0. So I zero out all of these entries below it, right? So I'm done with the first row, column. And then I move to the next row, right? And then I pick a non-zero entry and I pick it, and then I also make it equal to 1. Okay, and again, I keep the process when I zero out all the entries that are below this pivot position. So this is the pivot positions here, right? This is also a pivot positions. So as you see that all the entries that below a pivot positions will be 0. Okay, so I start from the leftmost pivot positions, and I will go down, right, and then go down to the next row. So start at the top left and start moving down, moving to the next pivot positions. For an example, if I have 0 here, right, this is a 0. And then if I happen to be, this is to be 0. And then this entry here is not 0. Then what I want to do, I want to make sure that the matrix is in the row echelon form. So I have to swap these 2 rows here. So then the last row will have more 0 leading entries compared to the third row, right? If I swap these 2 rows, then the 0 will be down here. And then this is not 0. All right. Let's see. And if I still have the 0 here, then just imagine that I still have another 0 here. Then I will move to the next non-zero entry of the third row, and I call it a pivot positions, and I want to make it equals to 1. And then once I claim a pivot position, I know what to do. I need to use row operations to make this entry here to be 0. All right. Once I run out of non-zero rows, right? That if there's no non-zero row left to modify this way, then I stop and I start with the rightmost pivot positions. So I start here. So I move from this pivot position on the leftmost pivot positions, I'm moving down, and then I stopped at the rightmost pivot positions. So from now, I start to work it back up. So I choose this pivot positions here. And remember, pivot positions is the only entry of the column when it's a non-zero entry. So that's why I have to work my way back up. I need to make this equals to 0, and I need to make this entry equals to 0, right? And then once I'm done with this column, I would move to this pivot positions, and then I'll make this entry to be 0. Okay. I don't have to worry about the third column because the third column doesn't contain a pivot position. So again, I only need to make sure that all the entries in the same pivot in the pivot columns will be 0 except the pivot position. So I have this is the pivot. I have 3 pivot positions here. I have 3 pivot columns, which is 1 pivot column here, right? And then the second one, and then the fourth one. Remember, the third column is not a pivot column. So this is the process on how you use the Gauss-Jordan algorithm in order to transform one matrix to its reduced row echelon form. So you work from the top left, work your way down to the rightmost pivot positions, stop. If there's no non-zero rows to modify, then you work your way back up from the right and then move to the next left pivot positions and 0 this entries and so on and so forth until you run out of rows to modify. Then you are done with transforming your matrix into the reduced row echelon form. Well, let's use Gauss-Jordan reductions to solve this two system of linear equations. First, I have a system of 2 equations with 2 variables. The first thing I want to do is I want to transform this system into its arithmetic matrix. But I have 1, -2, 2, -1, 3, and 9. Okay. And then the next things is I want to transform this arithmetic matrix into its reduced row echelon form. Okay. Well, I look at these 2 rows here. So the first row has the first non-zero entry on the first column. So I call this is, and it's also 1. So I call this is the pivot positions. Okay. Well, then my goal is I need to 0 out this entry here right below this pivot position in the same column using row operations. The row operations is I want to replace row 2 by, let's say, row 2 minus 2 row 1. Right. Then the result will be the first row will stay the same. The second row, 2 minus 2 is 0, -1 minus 2 times -2 is -1 plus 4 is 3. And 9 minus 6 would be 3. Okay. Well, now I look at this new matrix, the row equivalent matrix here. The first row seems to be okay, right? And now I move to the second row. So the second row, I have the first non-zero entry is 3. In order to put this matrix into its row reduced echelon form, we need to make it equals to 1 using a row operation. So R2 equals R2 divided by 3, right? So if I do that, then I will change my second row again into 0, 1, 1. All right, so this is my pivot positions. And at this point, I don't have any non-zero row to modify, so I stop and then start working my way back up. That means I start with this rightmost pivot positions, and I want to zero out this guy, this entry here, by doing a row operations. So I want to replace row 1 by row 1 plus 2, row 2, right? Negative 2 plus 2 times 1 is 2. Okay. Well, the new matrix is going to be 1 plus 2 times 0 is just 1, right? Negative 2 plus 2 is 0. 3 plus 2 times 1 is 3 plus 2 is 5. Okay, so that's the new row 1. And then row 2 stay the same. At this point, I ask myself, okay, am I done? Is this a reduced row echelon form of a matrix? And the answer, it is, right? As you can see that this matrix here is in the row echelon form. 1 is the first non-zero entry is 1, and then the second row has 1 more leading 0 entry compared to the first row. So, and then since these 2 here are pivot positions, and these 2 entries are the only non-zero entry of the first column and the second column. So then, yes, this is the reduced row echelon form. And from this form, I can solve for the system again. The goal is solving for the system using reduced row echelon form. So from here, I will know that x2, so from here, I can translate this matrix into a system. x1 minus 0x2 equals to 5, and 0x1 plus x2 equals to 1. Okay, so then what you have is x1 equals to 5 and x2 equals to 1 is my solutions. All right, if I want to write these solutions in the 2-tuple form, the solution will be 5 and 1. And you can read these solutions off of this reduced row echelon form. You say x1 equals to 5, x2 equals to 1, which is the solution for this system. Now we're going to look at this system of linear equations. So you have 3 equations with 3 variables, and we want to solve for this system using the Gauss-Jordan reduction. All right. Again, the first step is I want to translate this system into its augmented matrix. Okay. Now I want to reduce this matrix to its reduced row echelon form. I'm looking at the first column, the first non-zero column here, and I see that this position here is a good pivot position. All right. If it's a pivot position, then I need to zero out these entries and this entry using row operation. So which row operation should I use? Right, so I want to replace R2 by R2 minus 2R1, right? 2 minus 2 times 1 is 0. I want to replace R3 by R3 minus 7R1 because 7 minus 7 times 1 is 0. Okay, well, let's write out the new or the row equivalent matrix after these two operations. So this will be 0 as the goal, right? 3 minus 2 times -1, 3 plus 2 is 5. -1 minus 2 times -2, which is -1 plus 4. -1 minus 2 times 2, -1 minus 4 is -5. And you have 1 minus 2 times 4, which is 1 minus 8 is -7. In the third row, 7 minus 7 is a 0, which is the goal. 3 minus 7 times -1, which is 3 plus 7 is 10. 4 minus 7 times 2, which is -14. So 4 minus 14 is -10. 7 minus -7 times 4. So 7 times 4 is -28. 7 minus 28 is -21. Okay. All right. Now we so we got, this is the pivot positions. Now we move to the next row, and the first non-zero entry is 5. Okay. Well, what can we do? First, maybe we want to make this, we choose this as the pivot positions. And if it's a pivot position, you can either divide it by 5 to get 1 right now, or you can do it a little later. Well, let's do it now. So I want to divide R2 by 5. So then I will have a pivot positions that has 1 as the entry. 0, 1, -1, and -7/5. And then the last row stay the same. Okay. All right, and then now that I identify another pivot positions here. That means I need to zero this entries out, right? By using a row operation. So I want to replace R3 by R3 minus 10 R2. Because I use R2 because my the second row is a pivot row at this point. So the new matrix is the first row stay the same, the second row stay the same, and the third row will be 0 minus 0, just 0. 10 minus 10 is 0, which is the goal. -10 minus 10 times -1, which is -10 plus 10 is 0. And then -21 minus, say, -21 minus 10 times -7/5, which is, this is 2. -21 plus 14 is -7. Okay. Again, -21 minus 10 times -7/5, and then 5, 2 plus 1, -7. All right. Okay. Well, then now here I have one pivot positions. I have another pivot positions, and then I move to the next row. It's -7. Since it's -7 here, I can, and then this position should be the pivot positions. So that's why I want to make it equals to 1. So R3 will be R3 divided by -7. Okay, you have 1, -1, 2, 4, 0, 1, -1, -7/5, 0, 0, 0, and 1. Okay. Well, at this point, we can keep going. However, if you pay attention to the last row here, if you pay attention to the last row, if you translate this matrix back to a system of linear equations, what you have is you have, this is x1, x2, x3, right? And this is the constant. What you have right now is you have 0, x1 plus 0, x2 plus 0, x3 equals to 1. Is it true? 0 plus 0 plus 0 equals to 1. So this is the false statements. If it's a false statement, that means this system here will not have a solutions. So we can stop here, right? And then you can conclude that the system is inconsistent, which means the system has no solutions because of the last row that we figure out.